You know, when you look at something like the pyramids of Giza, or even modern supersymmetrical buildings, what's their secret? Well, a big part of the answer is a simple but really powerful shape, the isosceles triangle. And today, we're going to totally unpack it.
So here's how we're going to break this down. We'll start with the absolute basics, just to make sure we're all on the same page. Then I'll introduce you to some really cool tools that'll help you look at these triangles like a pro. By the end, you'll see how everything just clicks together perfectly.
Okay, so first things first. Before we can get into all the cool properties of these triangles, we've got to know exactly what they are. It all boils down to one simple, elegant idea.
And here it is. It's so simple. An isosceles triangle is just any triangle where two of the sides are the exact same length. That's it. Two equal sides. Lock that in your brain, because once you know that, you'll start seeing these things everywhere.
Okay, so let's put some names to the faces here. Those two equal sides we just talked about, we call those the legs. Think of them as the strong, supportive part of the triangle. And that third side, that's the base, kind of like the foundation. All right, now that we know what an isosceles triangle is, let's learn how to talk about it properly. You know, in geometry, getting the vocabulary right is half the battle. It's the key to really understanding what's going on.
So first up, you've got the legs. Those are our two equal sides. Simple enough. The third side, that's the base. Now the point where those two legs meet, kind of like the peak of a roof, that's called the vertex. The angle at that vertex is, you guessed it, the vertex angle. And then you have the two angles at the bottom, where the legs hit the base. Those are your base angles.
Okay, now this is super important. This is a trap a lot of people fall into. We're so used to seeing triangles sitting flat, with the base at the bottom, right? We just assume it's always the bottom side. But in geometry, you've got to be more precise than that.
And this triangle right here is the perfect example. Look, it's tilted on its side, but those little tick marks are telling us that sides AC and BC are the equal ones. They're the legs. So what does that make side AB? That's right, it's the base, even though it's not on the bottom. So the main takeaway here is the base is defined by where the legs are, not by how the triangle is turned. Okay, you ready to level up? Because we're about to add some really powerful tools to your geometry toolkit. We're talking about something called auxiliary lines. These are like the secret weapons of geometry.
So what are they? Think of auxiliary lines like a detective's magnifying glass. They're not originally part of the triangle, but we can draw them in to help us find hidden clues and really understand the properties of the shape. Now, there are a bunch of different auxiliary lines, but today we're going to focus on what I call the Fab Four, the four most important ones you're going to see over and over again in geometry. We're going to look at each one by one, and see what makes it tick. First on our list is the angle bisector. And the name pretty much gives it away, right? This line's whole job is to bisect or split an angle into two perfectly equal parts. Imagine you're cutting a slice of cake. The angle bisector is that perfect knife cut right down the middle, giving you two identical pieces.
So check this out. The line AD here, that's our angle bisector. See how it starts at vertex A and just slices right through the big angle BAC? It creates two new, smaller angles, angle 1 and angle 2, and they are perfectly equal. We say they're congruent, which is just the fancy geometry word for being an exact match.
All right, next up, we've got the median. And again, think about what a median is on a highway. It's that strip right down the middle of the road. Well, it's the same idea in a triangle. A median is a line that goes from a vertex straight to the midpoint of the opposite side.
And in this picture, the line segment AM is our median. It starts up at vertex A and makes a beeline right for point M. And what's special about M? It's the exact middle of the opposite side, BC. The median's only job is to find that midpoint and connect to it, splitting that side into two equal halves. Okay, now this is a really important point, so pay attention. A median and an angle bisector are not the same thing. In most triangles, they are two completely different lines that do two completely different things. It's super easy to get them mixed up, so make sure you keep them straight in your head.
Our third line is the altitude. The easiest way to think about this one is as the height of the triangle. You know, if you wanted to measure how tall the mountain is, you'd drop a measuring tape straight down from the peak to the ground, so it makes a 90-degree angle, right? That's exactly what an altitude does in a triangle.
And this image makes it crystal clear. That line AE is the altitude coming from vertex A. It drops straight down and hits the base BC at a perfect right angle. You see that little square symbol at point E?
That's the universal sign in geometry for a 90-degree angle. Whenever you see that, you know you're looking at an altitude. And that brings us to our fourth and final key line, the perpendicular bisector. This one is like a super combo, a real powerhouse. Why? Because it does two jobs at once. It's perpendicular, meaning it forms a right angle, and it's a bisector, meaning it cuts a side exactly in half.
And here it is in action. Look at the line FM. It hits the side BC right at its midpoint, M, so it's a bisector. And it hits it at a perfect 90-degree angle, so it's perpendicular. It's a 2-for-1 deal, and that's what makes it so useful.
Whew, okay. We have covered a lot of ground. We've defined what an isosceles triangle is, we've learned all the names for its parts, and we've met the Fab 4 auxiliary lines. So now it's time to put it all together and see the full picture.
This slide is where it all connects. We see all four of our key lines in relation to the same triangle, and each one has its own unique role. You've got the angle bisector AD splitting the vertex angle, the median AM connecting to the midpoint, the altitude AE dropping down to form a right angle, and the perpendicular bisector FM, which hits that same midpoint also at a right angle. 4 different lines, 4 different jobs.
So we've really built a solid foundation today, but honestly, this is just the start of your adventure in geometry. We've seen how these 4 lines act in a sort of generic triangle. But what do you think would happen in a more special case, like, say, an equilateral triangle, where all 3 sides are equal? Do you think these lines would still be separate? Or would they all merge into one? Something to think about. Thanks for tuning in, and never stop being curious.